Precision, speed, repeatability. CNC machines are the backbone of modern manufacturing. From aerospace to jewelry, CNC transforms designs into parts with minimal human touch. Today we'll trace CNC's history, how it works, major applications, and where it's headed. We'll cover the tech, the industries, and practical implications for manufacturers. Let's get started. Narrated by a manufacturing professional perspective. First, a bit of history. Where CNC began. CNC traces its roots to the 1940s and 50s when numerically controlled, or NC machines were developed for military needs. Early systems used punch tape to control machine motion. As computers advanced, NC evolved into CNC, bringing programmability, flexibility, and automation. Key milestones: computer control, multi-axis machines, and integrated CAD/CAM workflows. The result was a productivity leap, complex parts with fewer errors and faster throughput. Design moved from paper to pixels, enabling direct translation to machines. That digital bridge, CAD to CAM to CNC, set the stage for the industries we'll examine next. Now, how CNC actually works, let's break it down. It starts in CAD, where parts are designed in 3D. CAM generates tool paths, the planned movements the machine will follow. CAM outputs G-code, the language that tells the machine positions, speeds, and feeds. Operators load the program, set offsets, and start the automated cycle. Multi-axis machines can move tools and parts simultaneously to create complex geometries. Automated tool changing optimizes cycle time and allows varied operations without stopping. In-process probing ensures dimensional accuracy and reduces scrap. CNC works with diverse materials: aluminum, titanium, composites, steels, each needing tailored feeds and tooling. Robotics integration enables lights-out operation and higher throughput. Connected machines provide real-time data for monitoring and predictive maintenance. Simulations reduce risk before cutting metal, saving time and material. With that, let's look at where CNC makes the biggest impact. Aerospace demands extreme precision and traceability, areas where CNC excels. Engine components require tight tolerances and complex forms. CNC handles advanced materials like titanium and composites used in aircraft. Hybrid workflows let engineers prototype fast, then finish parts to aerospace standards. In-process inspection and certification documentation are built into aerospace workflows. Traceability from CAD to finished part ensures compliance with safety standards. The result? Safer, lighter, and more reliable aircraft enabled by CNC precision. Next, automotive manufacturing. Automotive relies on CNC for engine blocks, transmission components, and critical tolerances. Precision gears and shafts must meet exacting specs for performance and efficiency. Robots tending CNC machines increase throughput while lowering labor costs. One operator can manage multiple cells, boosting productivity. Custom and performance vehicles use CNC for bespoke components and tight tolerances. Racing and luxury markets depend on CNC for repeatable, high-quality custom parts. Across mass production and niche manufacturing, CNC ensures fit, finish, and reliability. Now, medical and electronics. Medical devices demand micron-level precision. Think implants, surgical tools, and dental parts. Materials and traceability are critical for patient safety and regulatory approval. Miniature parts, dental crowns, and tiny connectors are feasible with micro-CNC tools. Repeatability means consistent outcomes across batches. In electronics, CNC makes precise housings, connectors, and prototypes to tight tolerances. As devices shrink, accurate machining of small features becomes indispensable. Hybrid manufacturing combines strengths of additive and subtractive methods. Higher quality, fewer defects, and easier regulatory compliance are common outcomes. Next, we'll cover woodworking, jewelry, construction, marine, and energy uses. CNC routers revolutionize woodworking with repeatable, intricate carving for furniture and mass custom orders. Mass customization brings bespoke designs to scale. Jewelry and fashion use CNC for delicate, repeatable patterns that were once hand-carved. Designers iterate quickly with CAD models and precise machining. Architecture uses CNC to fabricate structural and decorative panels from steel, stone, and composites. Digital fabrication enables forms that were previously impractical. Marine components require corrosion-resistant materials and precise balances. CNC provides both. Energy infrastructure parts, wind and gas turbines, depend on CNC's ability to handle large, exotic materials. Across diverse industries, CNC scales from tiny components to massive structures. Major producers include Haas Automation, DMG Mori, Mazak, Okuma, and Fanuc, among others worldwide. Common machine types: vertical and horizontal machining centers, lathes, and multi-axis systems. Machines vary by features, tool changing, thermal compensation, and real-time monitoring. Options range from desktop hobby machines to multi-million-dollar production cells. Emerging manufacturers from China and South Korea add competitive options and expand global capacity. Choosing the right machine depends on parts, materials, and production volume. Costs vary. Machine type, material complexity, and volume determine per-part economics. High throughput reduces per-unit costs. Smaller shops may face higher barriers to entry. Training in G-code, CAD/CAM, and machine operation is essential. Vocational programs bridge the gap. Online resources and simulators make training more accessible. Sustainability concerns include energy use and coolant disposal, but recycling and efficient machines help. Maintenance and skilled labor remain ongoing costs and operational challenges. Lower-cost machines and open tools are lowering entry barriers for small businesses. Industry 4.0 brings IoT, sensors, and AI, enabling predictive maintenance and adaptive machining. Hybrid systems combine additive freedom with subtractive accuracy for best-of-both workflows. Augmented reality and better interfaces will make advanced machining more accessible. As these technologies spread, global manufacturing becomes more precise, efficient, and innovative. CNC machines bridge digital design and physical reality, shaping products across industries. If you're in manufacturing, explore CNC workflows, invest in training, and adopt data-driven practices. Subscribe for deep dives and resources. Thanks for watching.